In this exercise, we're going to talk about ANSI specs versus ASME specs when it comes to tolerance dimensioning. So at the bottom of the sheet, we're going to identify what these numbers should be. Um, this is an example of what an ANSI drawing might look like. This is the call out. Here, the tolerance block. They'll have a note generally referencing that this is an ANSI type drawing. And this tolerance means that if there's a dimension to one place, that it is 0.1 tolerance, meaning that if it were 10 inches, it could be 10.1 long or 9.9. So if you have a plate and you measure off a dimension 10 inches, if the plate is over 10.1, it is too long. And if the plate comes in short, 9.9 would be the minimum. If it went to 9.8, you would have to scrap it and make a new part. So that's how tolerance works. If there's two place call out on a dimension, which is typically what they leave on a engineering drawing for mechanical structural type parts, you have a tolerance of plus or minus 0.3. That means plus 3 minus 3, meaning the tolerance is really 0.06. Three places 0.01, 0 tolerance, and four places 0.005 tolerance. Now, when you're out in the field, when you say that there's a two-place tolerance, nobody says plus or minus 0.03. Nobody says 300ths. They say 30 thou. They don't even pronounce thousands. It's just 30 thou, or three places is 10 thou, and four places is 5 thou tolerance. So a drawing may look like this, where this dimension has three places, telling the shop, hey, this is a more critical dimension, this is a more critical dimension. This dimension of 2.50, the greatest value it could be is 2.53, and the smallest value it could be is 2.47. Whereas this one here, since it goes to three places, you can only add 10 thousandths tolerance. So this could be 1.38 to minimum 1.365 condition. So maximum condition is 1.385, minimum 1.365. All right, so if the hole doesn't land in between those numbers, you have to scrap it and try again. So we try not to throw these tolerances on there and make that tight, but sometimes we have to in order to get things to fit. So this hole might be aligning with something else, and it might be flush to this edge. So whatever the mating piece is, that dimension, it's got to also come from here to this hole. If they don't dimension them the same, we're probably not going to get these holes to align, or if there's a pin that lines up to the hole or whatever. So that's why you might see a more critical dimension to locate the holes. They're calling off three places here, making the hole location the most important thing, and the rest of them just are 30 thou across the board. Comparing that to an ASME drawing, there is no tolerance block. They just put in the notes, everything is 30 thou unless we specify differently. All dimensions are just presumed plus or minus 30 thou, unless they call it off like this. So to do the same thing on an ASME drawing as we did on an ANSI drawing, all dimensions are four places, and they're all plus or minus 30 thousandths or 30 thou. Now, these dimensions actually call off the tolerance that they want for this dimension. If this were a ANSI drawing, these four place callouts would represent plus or minus 5 thou, 0.005. But really, I don't want 5 thou, I want 10 thousandths or 10 thou on these here, and then 30 thou on the rest. Okay, so if you compare this to this is old school. I like it because there's two places. It's simpler, easier to see the drawing. But then you have to always change these precisions. You got to remember which ones to change for precision. The one thing that's always caused a lot of controversy with the two-place dimensioning is 0.56. How are you supposed to know that's 9/16ths? I'm old school, I've been around the block. Plus, I know they don't have a cutter that's 0.56. There's no drill bit out there that's 0.56. When you go to the store, when you run down to Ace Hardware or McClendon's, you've never asked for a 5.56 bolt, right? You would ask for a 9/16ths. Having it called off 4 places removes all the controversy about whether or not that's 9/16ths or whatever. So you see 5625, that is the decimal fraction or decimal for the fraction 9/16ths. I know that 3/8 up above is what it would have been called. 1.3 is, if they would have called it 1.38, it'd be controversial. It's like, is that really 1 3/8? Is this really 7/8? Well, when they put out 0.8750, there's no doubt it's 7/8. You can see the 4 decimal places. So you're going to fill in the fractions and the actual numbers. You're going to edit this, and then you can submit it, and it goes all off of these. So what are the fractions for each one of these? All right, and I gave you example for number one. Number one is 2¼ inches, and the ASME call out would be 2.2500 because it has to have 4 places. All right, I'm sure you'll do well on this quiz, so please fill this out and submit that.